So this problem is asking us to do two different things. The first being solve for the time required for the bearing friction to stop the blade. So we're going to call that part A, and we'll do that first. So we're going to write down what we know from the start. So we know we have this angular velocity initial of 1,500 rotations per minute. But we want that in radians per second, so we're going to convert that. So 1,500 rotations per minute. And we're going to multiply that by 1 minute over 60 seconds, because that'll get rid of the minutes. And then we're going to multiply that by 1 rotation, 2 pi over 1 rotation, because there's 2 pi for 1 full rotation of a circle. And then that gives us 157.08 radians per second for our initial angular velocity. 0.08. And then we also know that we have a combined weight of 3 pounds, and a radius of gyration of 1 inch. And 1 inch is equal to 1 divided by 12 feet, so 1/12 of a foot, because there's 12 inches in 1 foot. So then it asked us, what is the time required for the bearing friction alone to stop the blade? And then we also have that our force of bearing friction is going to be negative 0.015 inch pounds, and that's negative because it's opposing the motion of the saw. So from here, we're going to write down our angular impulse. So delta K is equal to moment of inertia times the final angular velocity minus initial angular velocity times impulse as well, or moment of inertia, sorry. And so we know that our angular impulse is constant, so we can substitute moment. We can this is equal to moment times time, because it's constant, and we know that our moment of inertia is not going to change in this scenario, so that's going to stay constant. We can pull that out front, and it'll leave us with our final angular velocity minus our initial angular velocity. So our I value that we're using for this case is equal to mr squared, and then our final angular velocity is going to be 0 because it's coming to a stop. So we can start to plug this in. So the moment is, it's also important to note, our moment is equal to our force times the radius. So we have all these values, so we can go ahead and plug them back into here. So our moment here is going to be the force of T, negative 0.015 times the radius, which is 1/12 feet, times the time. We don't have time, but that's what we're solving for. And that's equal to our moment of inertia. Our mass is going to be 3 pounds divided by 32.2 feet per second squared, because that's mass. We had weight, and to go from weight to mass, we're divided by 32.2 feet per second squared, or the acceleration due to gravity in English units, because that's what we're using for this problem. And then we multiply that by our radius, which is 1/12 feet squared, and our final angular velocity is 0, so we're just going to be multiplying by negative 157.08 radians per second. So when we do this, we end up getting our t value is equal to 81.3 seconds or 1.35 minutes. And this is with no brakes, just friction from our bearing friction. So this is our time it takes in part A. So now we're going to do part B. So part B is the second part, and it's asking what is the torque a braking system would need to apply to stop the blade in just 0.25 seconds. So we pretty much have the same information. We have the same starting speed. We have the radius is the same. Our weight's the same. Our final speed will be 0 still. And then we have a time now, though, and that's 0.25 seconds. And then our moment of inertia is going to stay the same, mass times radius squared, and then we're going to use the same equation as we did. It's going to be the same variables, just different numbers. So we have moment times time is equal to moment of inertia times final speed minus initial. This is still 0. And this is exactly the same as before. So same as A. So from here, we're just going to plug in our other values. So we're going to solve for moment, so we don't know that. So but moment times 0.25 is equal to 3 divided by 32.2 times 1 divided by 12 squared times negative 157.08. And that leaves us with our moment is equal to negative 0.406 foot-pounds, or it's also equal to negative 4.88 inch-pounds. And this is our answer to part B, and this is with the brakes. So there we solve for both A and B, and we have the moment needed and our time from part A.